Hello everyone, today I am finally going to make an explanation video again. However, I am not quite yet continuing my Scramjet series yet. Instead, I wanted to take the kind of fitting time right now. I will reply to a request and kind of widen out that topic. So today I will finally explain to you how electric space propulsion works, or what different kinds of electric space propulsion systems there are, and how each of them works in response to a request to explain how Arcjets work. Now there are four main types of electric space propulsion systems, which again can be subcategorized but can also be over-categorized. There are two categories that are actually practically useful right now. Then there is one category that is a bit more far-fetched. Actually, it's not really far-fetched, but its actual usefulness is still limited by its performance, and it's basically still an engineering challenge and will maybe become useful in the future. And one is a rather exotic space propulsion system, one of these more specific systems that only work under certain circumstances like solar sailing, and is also not currently really in use for anything. Now I'll start with the first two, the first of which are electromagnetic or electrostatic engines, which basically contain the most well-known electric space drives, the currently also most used electric space drives, the ion engines. And they're basically all ion engines. There are, of course, some special types of ion engines. What they do is actually to use electromagnetic or electrostatic effects to accelerate ionic particles or ionized gas. The propellant here is any gas, usually one that is well suited for this, often xenon, and this gas is ionized, so the atoms of this gas are charged, and then they can be accelerated by an electrostatic effect with two electrodes, or more or fewer, depending on what specific type of design you make. You can add magnets or electromagnetic spools to guide them or to guide them in circles to gain more cycles of acceleration and increase your specific impulse. But the basics is always that you use an electrostatic effect, an electric field, to accelerate charged particles, which are then your exhaust, your propellant. They propel your spacecraft in the opposite direction according to Newton's third law as you accelerate them backwards. They can reach extremely high specific impulses, so they can be extremely propellant efficient, but actually all these electric engines are energetically really efficient, but that still means they're limited by the conservation of energy plus a little thermal loss. So high specific impulse means that you need a lot of energy per thrust, as you have to apply the force that is your thrust over a higher velocity. Now, of course, the specific impulse of ion engines can be throttled, essentially. It's not really the engine throttle, but you can reduce the specific impulse of a ion engine by design, or in some models of ion engine also during the flight, which does give you a better thrust to power consumption ratio in exchange for a worse thrust to fuel consumption ratio or propellant consumption ratio. But it does make the engine unoptimal, as the thrust weight ratio in ion engines is usually not that great, and if you reduce the specific impulse of an ion engine to be around that of a normal rocket engine, you'll obviously come out at a much worse thrust weight ratio. So it might be better to use a different type of engine if you don't really want an extremely high specific impulse. These actually range up to 6,000 seconds easily. The second type of electric space propulsion system is the thermal electric engine, which actually is by definition an electric rocket engine and is also what was originally asked for. Now these perform somewhere pretty much in between the ion engine and the ordinary rocket engine, and they also work a bit like a ordinary rocket engine, although their performance is a bit closer to the ion engine. What they do is actually to heat up some sort of propellant using an electric effect or an electric heating system, and then expand it through a nozzle, just like any normal rocket engine, and then propel it and gain thrust through the expansion through a nozzle, just like a rocket engine, just except heating it up by chemical reaction in a combustion chamber. It instead heats the propellant up by an electric effect on electric heater, which can reach high temperatures while using pure hydrogen or pure helium as a possible propellant, and thus can reach really high specific impulses of up to 1,500 seconds or even 2,000 seconds. Of course, these can be theoretically combined with a normal rocket engine. You could have electric heating plus a chemical reaction, but that would drastically reduce the actual advantage of a electrothermal engine, because the big advantage is that you can heat up your propellant, but the propellant can be a really light element like hydrogen, which then gives you a really high specific impulse for your temperature. And to reach such a high specific impulse with a fuel mixture that actually contains an oxidizer and actually burns as well would mean that you would also have to reach really high temperatures. So theoretically, combining a electric heating with a chemical rocket engine could give you a better specific impulse than a normal rocket engine, but practically, in order to reach a significantly higher specific impulse than a normal rocket engine, you'd need incredibly hot combustion chambers and nozzles, and that is just simply not quite practical yet. Then, of course, there are different types of electric heating engines. There are the actual Arcjets, which are relatively popular. They're mainly developed at ERS, which is the Institute for Spaceflight System, the German acronym meaning Institut für Raumfahrtsysteme at University Stuttgart, where I actually study. And there are several test models bound to fly within the next time on a small communication satellite and on a lunar probe. And Arcjets heat their propellant by using an electric arc. They have two electrodes, usually one of the electrode being the inside of the nozzle itself, which of course then has to be limited to the beginning of the nozzle. You don't really want to extend that electrode all the way to the edge of the nozzle, which is, there are several techniques how you can do that. Usually there's a gas film used to do that, and the other nozzle is essentially a rod inside the fuel injection or inside the nozzle, and between these electrodes you have an electric arc, basically like lightning, and you use that to heat up the fuel, which is not only quite powerful for its weight, but also really efficient, since the electric arc mostly heats up the fuel actually, because it's the arc itself only is in the fuel itself. The arc is basically a property of the fuel, So the fuel essentially heats itself, and most of the resistance is in the arc, so most of the power gets lost in the arc. So most of the heating actually hits right in the fuel or in the propellant. And there is a different main type of thermoelectric engine, which is the resistor heated engine, which actually uses some type of resistor, essentially a block of material that has a relatively high but not too high electric resistance, and you push electricity through it and it gets hot, and then you can hold that hot resistor into the propellant and thus heat the propellant up, which is less efficient but simpler to design in some ways. And of course there are theoretically other ways to heat up propellant electrically. Now the third main type of electric space propulsion system is a bit more exotic but actually really simple. It's basically a light bulb or a radio dish. You can actually directly use light as your propellant. Now, this can spark discussions in Facebook comments between people who think they know physics, but it is actually long proven that light has an impulse that's in our standard model of physics. Light does not have mass, yet it does have an impulse, and people will bring up the equation for impulse, which is mass times velocity, but that equation is only in Newtonian mechanics and not in actual relativity. So for speeds approaching the speed of light, that equation is no longer exactly true. And at the speed of light, you actually can't have anything with mass at the speed of light, but at the speed of light something can actually have impulse but not mass. It actually has impulse according to its energy converted to mass by the equation of relativity. It sounds complicated, but what it basically means is that light doesn't have mass, but it has energy and it has impulse, and its impulse is essentially its energy divided by the speed of light, which is rather small since the speed of light is huge, so anything divided by the speed of light ends up being rather tiny. But yes, it does actually mean that anything giving off light or any electromagnetic radiation does actually have a certain knockback according to Newton's third law, which does actually still hold true in relativity. Uh, of course, many light sources give off light in several directions and so on, but you can use mirrors, or you can use a radio dish or a specially designed antenna, and you can direct electromagnetic radiation or light or microwaves or radio waves or gamma rays or infrared radiation or ultraviolet radiation, whatever you like, into one direction and get a Newtonian recoil and gain thrust through this. Of course, it does have a very low power consumption, thrust to power consumption ratio, a very high power consumption to thrust ratio, as that ratio is the speed of light. That is still assuming a very efficient light source, but most light sources are actually very energy efficient, which does limit your thrust weight ratio already because you need a heavy power source, and then the thrust weight ratio of the light source itself is usually not that great. So yes, that does kind of demystify the EM drive. The EM drive is basically a glorified microwave. The reason that it is said to be or appears to be physically impossible is not because it doesn't use any propellant or any propellant with mass. The reason that it seems physically impossible is because there seem to be no radio waves escaping it or no microwaves escaping it, but there are and that is actually getting really complicated. The microwaves basically escape it without being measured as escaping it, and that's where it gets really complicated and not quite yet understood. But the idea of fuel-less propulsion is not physically impossible and not new, and the EM drive isn't very good at it either. It has a worse power consumption to thrust ratio than basically any radio dish. But it is quite interesting because it's not yet quite understood, so we might learn something new about physics from studying it, and that might then help us design better space propulsion systems. But that's still far off in the future. Then the fourth type of electric space propulsion is a bit more exotic. It's actually as it doesn't really give you a thruster that you could put on a spacecraft and you turn it on and it produces thrust in its opposite direction, and you can have several thrusters and maneuver your spacecraft and apply thrust, but rather it uses outside circumstances. That's the magnetic field-based propulsion, where what you essentially do is you use electromagnetic effects to propel yourself against an outside magnetic field. So it actually is comparable in some ways to a solar sail. It does use outside circumstances. You can use any magnetic field, like the magnetic field of Earth, or the magnetic field of any other celestial body, or a magnetic field supplied by a space station with an electromagnet, depending on what you need for your specific concept. But the idea is to use that magnetic field to move a spacecraft, which I am not going to explain in full detail, but there are several ways, of course, you can do that, and depending on what type of electromagnet you have on board and how you use it, you can then, for example, pull yourself towards another magnetic field source or away from the source of the magnetic field, or actually perpendicular to it, depending on what kind of equipment you have and what kind of concept you're actually making. But they're not really in any practical use anywhere in the near future. So this was a brief overlook of the types of electric space propulsion systems there are. I hope this was kind of interesting for you. I'm always open to requests or questions, and as always, thanks for watching.